Okay, Assalamualaikum and a very good afternoon to all the students. Uh, for first of all, I would like to say sorry because I couldn't make it as a physical class. Yeah, so we can have only through online class. Yeah, due to my commitment to others, things. So I really feel sorry for that. So but I hope that this video will help you to understand chapter 6 properly and also will help you to answer for final exam. Yeah. If you have any questions regarding to chapter 6, please come and see me. Yeah. I am my room is really open to you and you can come, but please contact me first and set the appointment. Yeah. Okay, as I promised, we need to complete chapter 6, the last chapter for the whole syllabus. Yeah. We still have chapter 6 to complete. So chapter 6 is the influence line for statically determinate structures. Yeah. Okay, as usual, in each chapter we have subtopic. So this chapter 6 we have 7 subtopic that you need to understand. Yeah. So the first one is the influence line. The second one, influence line for beams. Third, qualitative influence line. Fourth is the influence line for floor girders. Number 5, influence line for trusses. The second last of subtopic is the maximum influence at a point due to a series of concentrated loads, and the last one is the absolute maximum shear and moment. Yeah. And as usual, in each chapter, there are certain objectives that you need to achieve or you need to achieve. Yeah, you need to understand. The first objective is to show how to draw the influence line for statically determinate structure. So you can see the keyword here. This chapter 6 is only applicable to a statically determinate structure and provide specific applications to floor girders and bridge trusses. And then the second objective is to determine the maximum live shear and live moment in a beam or bridge girder that support several concentrated loads. Yeah. So influence line is normally popular or normally used for structural engineer in order they want to trace or they want to see at which point along the bridge have a higher moment or have a higher shear. Yeah, instead of using bending moment or shear force diagram, you can also use influence line if you want to predict at which point to have higher moment or higher shear force. Yeah. Okay, there are two objectives that you need to achieve at the end of this chapter. Okay, we go first for the first subtopic. Yeah, we go for the first subtopic, which is influence line. So normally for influence line, we will use for a moving load. That's why I just now I did mention this method or this procedure. Influence line is more applicable to bridge structures because you have a vehicle moving, yeah, along the bridge, so it can be considered as a moving load. Yeah. So if a structure is subjected to a moving load, the variation of shear and bending moment is best described using the influence line. Yeah. Unless you have a static point load, then it's easier, rather than to use the influence line, it's better to use bending moment and shear force diagram. But for bridge, normally we will use influence line. Yeah. So by using the influence line, where the moving load should be placed on the structure so it creates the greatest influence at a specific point. Yeah. So the magnitude of the associated shear, moment or deflection can be calculated or can be achieved and shown through this influence line diagram. Yeah. So this is the best method if you want to predict the behavior of the moment, the shear for a bridge. Yeah. Okay. So you need to make it clear what is the difference between influence line and shear or moment diagram. Yeah. So influence line represent the effect of a moving load only at a specific point. Yeah. Because when you have a car moving along the bridge, so you can know what is the shear or moment at one point along the bridge. Yeah. But it's different with the shear and moment diagram, because shear and moment diagram you will draw the whole behavior of the bridge. Yeah. Because it says here represent the effect of the fixed load at all points along the axis of the member. So shear force and bending moment diagram will show what is the value of the moment along the bridge or along the element. But influence line, it only shows the shear or the moment at one specific point. Yeah, so that's the difference. Yeah, influence line only at a specific point, but moment and shear diagram show along the axis of the member, along the points. Yeah, so that's the two clear things. That's the difference. Yeah, between the shear moment diagram and the influence line. Okay. To find or to calculate the influence line, there are two procedures. You can use, the first one is using tabulate values, and the second one is the influence line equations. Remember, there are two approaches. You can either use tabulate values or influence line equations. There are two methods. Okay, now we move to the first one, which is tabulate values. So it's already mentioned here, tabulate. So means that you need to draw or you need to do a table. Yeah. So how to calculate using these tabulate values? First of all, place a unit load at various locations along the member. Yeah. And then at each point, you can use static to determine the value of function at the specific point. Yeah. If the influence line for a vertical force reaction is to be constructed, then you need to consider the reaction to be positive at the point when it acts upward on the beam. Yeah. So you need to use the same concept as we used before this. Yeah. So same thing goes to the shear and moments influence line. Yeah. So you can take shear and moment as positive according to the sign convention that you used before this in previous chapter. Yeah. So here, I hope that you still remember this diagram that we already used in the previous chapter. Yeah, I think chapter 2 or let me see. Chapter 2 and chapter 4. Yeah, when we want to draw the shear and moment diagram. So in this influence line, we're still using the same sign convention. Yeah. So you can see here, normal force. Yeah. Going to the left, going to the right is positive, and going to the left is negative. And also here, the shear force. Yeah, so the shear again rotate. Yeah, the rotation is according to the clockwise, so consider as a positive. And here for moment, yeah, this is the sign convention that we consider as positive. Yeah, so this is positive, this one also positive. Yeah, okay. So as I mentioned just now, since the approach is using tablet values, and of course you need to draw a table. Yeah, so it is recommended that one first construct a table listing unit load at X versus the corresponding value of the function calculated at the specific point. Yeah, so we can straight away later on see the example. Yeah, so from there you can know what is the tabulated values means. Yeah, okay, now we move to the second approach, which is called influence line equations. The second approach is that you can construct the influence line also still by using a unit load. Yeah, placing a unit load at a variable position, yeah, at any distance. So you can choose the distance and call it as X. So once you put the distance, then you can compute or you can calculate what is the reactions. Yeah, the reactions, the shear, and the moment at the point as a function of X, because the distance you assign it as X. Yeah, the spans. So from that equations you can construct the influence line. Yeah. Okay, now we move to example 6.1. So this example 6.1 is in page 239. Yeah, 239. So you can refer to page 239. Is a beam. Yeah, construct a simply supported beam here. Construct the influence line for a vertical reaction at A, yeah, point A, at support A of the beam shown in this figure. So you can first choose to calculate using the first approach, yeah, tabulate values. So first of all, you need to draw the table, but to fill in the table, you need to place a 1 unit load, on the beam at each selected point. Here, since the question asks you to construct the influence line for the vertical reaction at A, so that's why you start with starting with A. So as mentioned just now, starting from A, and then you can place 1 unit load. In this example, they place 1 unit load first at X equal to 0, which means that you put 1 unit load here, starting here, 1 unit load, and then you need to calculate what is the reactions. Yeah, so then put all the values in the table. So you can see here X equal to 0, so put this 1 unit, and then you can determine what is the value for AY. Do the submission moment at BY, and then you can have AY. What is AY? Yeah, so automatically you know AY is equal to 1, and then you move the 1 unit to X equal to 2.5 meter. Then get the AY here. Yeah, so you can do you can calculate the AY. Yeah? First second 0.75. Yeah, and then you move again the 1 kilonewton, the 1 unit of point load to a new point. Yeah? So now in this table, they move another 2.5 meter, which is mean that the point load of 1 unit is being placed in the middle of the beam. Yeah? So you can see here 5 meter. So by putting this 1 unit, then calculate what is AY. Yeah? Then put this AY into this value. So you can do that every 2.5 meter. Yeah? You can see from this table, start from 0, 2.5, 5 meter, 7.5 until the rest of the beam, yeah, at 10 meter. So every point you calculate and get the AY. So once you have this AY, then you can plot the influence line. Yeah. So this is to answer the question, what is the influence line, or construct the influence line for the vertical reaction at A. So means that you put the 1 unit starting from A and then move until the rest of the beam. So this is the influence line for AY. Yeah. Okay. This is the first approach. You can also construct the influence line at A using the second approach, which is using influence line equations. Yeah. As mentioned just now, influence line equation means that you can put your 1 unit at any distance. So you can call the distance as x. Yeah? So by putting 1 unit at any distance, yeah, x. So then you do submission moment like this. Yeah? So you do submission moment at B, you can have AY times the distance, yeah, and the rest, then you can have this AY. So this is the line, this is the influence line equation for constructing the value at AY. Yeah? For constructing the influence line at AY. Yeah? So you use this value. So by putting, let's say you want to move 1 unit at 2.5. So you just substitute AY equal to 1. 10 minus, multiply with 2.5. Then you can have 0.75. Yeah. So you can check the result is still the same. Yeah. Your AY is still the same at x equal to 2.5 meter. Then you can plot. So end up you will have the same influence line, the same diagram. Yeah? So you can choose either to use tabulate values or you can use influence line equation. Okay. Now we move to example 6.5. So 6.5 is to construct the influence line for the moment at point C. Yeah, here. You need to construct the influence line at point C of the beam in figure 6.5. So since the question asks you to construct the moment, so means that you need to apply 1 unit of moment at point C. Okay. So you can use here the first approach, which is tabulate values, yeah, using table. So at each selected position of the unit load, the moment MC is calculated, yeah, because the question asks you to find moment at C. Okay, so you know is, you can check again, your C is happen to be at the middle of the beam. Okay, 5 meter. So now you can move every, let's say in this example, they start with 0. Yeah, place 1 unit at 0, x equal to 0, and then find the moment. Yeah. So when you place the 1 unit, then find the moment. Yeah. here. When you place one unit, first of all, you need to find the support reaction first. Yeah, this is the support reaction. So once you have the support reaction, then you can calculate what is the MC or moment at C due to one unit. Yeah, so you can move around starting from 0 and then 1.5. Yeah, let's say here you put one unit here and then you cut this. Yeah, because C is at the middle of the beam. Yeah, do the submission moment because you want to find the moment C. Yeah, do the submission, and then based on this, when you cut the beam, yeah, that's what I mentioned to you just now. The signage of the MCVC is still similar in chapter 4. Yeah, when you cut the section, you want to find MC here. Yeah, so you want to find MC, do the submission moment and at MC. So when you do submission moment at MC, this VC can be cancelled out. Yeah, so you can have this MC. So put the MC value here. Then do again, place this, yeah, at 5 meter. One unit at 5 meter. So this is 0.75 and this is 0.25. Yeah, then you cut the section. VC and then MC. Okay, and then you calculate that. So you will end up, when you move one unit at 5 meter, you end up your moment at C is 2.5. And then you do again, move the one unit at 7.5, one unit at 10 meter. Yeah, and that you will have this diagram, influence line for moment at C. Okay. So the second approach is to use influence line equations. Okay. So you can determine the two line segment, yeah, like this. This is what we call first line segment and this is the second line segment. So you already have this diagram based on the first approach. Yeah. So in case you want to check whether your diagram is correct or not, you can also use the second approach, which is influence line equations. Yeah. Okay. So the two line segments for the influence line can be determined using submission moment at C. Okay. So when you place, remember for the second approach, you can place one unit at any distance. Yeah? Here, they put at X. Okay. So once you put at X, cut the section and then find this MC, like this. Okay. So this happen to be your one unit point load is being placed in between 0 to 5 meter, and then cut the section and then you can have this equation for MC. Okay, so this equation is valid for this first line. Okay, how to come up with the second line, which is the second one? Yeah, so that's why you place your one unit in between 5 meter to 10 meter. Okay. So when you place your one unit in between 5 meter to 10 meter, so end up you will have this. Do the submission moment, then you can have this equation. Okay. So you have this equation. This equation represents this to create this second influence line. Yeah? So you just substitute again x equal to 0, x equal to 2.5, x equal to 7.5, and x equal to 10 meter, and that you will have this, the same diagram, yeah, this diagram. Okay, so we're done with 6.1. Now we move to 6.2. Influence lines for beams, yeah. So once the influence line for a function has been constructed, it will be possible to position live loads on the beam, which will produce the maximum value of the function. Normally for beam, we have two types of loading. We have concentrated load like this, point load. So this is what we call concentrated load. And then the other types that common use is the uniform loads, which is like this. You have uniform distributed load along the beam. So these are the two common types of loading, that we always consider for beams. Okay. So now we want to see how to create a influence line for a concentrated force. Okay. So remember here, for any concentrated force, F, and this is the concentrated force, acting on the beam, the value of the function can be found by multiplying the ordinate of the influence line at position at by magnitude of F. Yeah. So means that, let's say consider figure 6.7 here. Yeah. You have point loads or concentrated load being placed at the middle of the beam. Yeah. How to calculate, how to construct the influence line for AY. Okay. So you know that if you place one unit here, automatically this one will be half. And this one also will be half. Okay. So for a force, means that your value half this one multiply with F. Yeah. Okay. So this is the value for influence line for at Y, for influence line for AY. Yeah. So your influence line for AY is half times the force. Okay. Depends, if your force is 2 kilonewton, then half times 2, and so on. Yeah. Okay, now consider for the uniform load. Uniform load means distributed uniform load. Yeah. So here I will straight away go to this diagram. Yeah. Let's say you have a uniform distributed load and you want to calculate what is the influence line due to this. Yeah. So normally this one you can create, you can calculate the shear force. The load creates a concentrated force using this equation. So the effect of this concentrated force is determined by integrating over the entire line of the beam. Okay. So for example here, like this. You have a uniform distributed load, and then you want to calculate what is the influence line for AY. Okay. So to calculate the influence line for AY means that you have to calculate the area here. Yeah. The area here, half times 1, times the distance, and multiply with the value of the distributed load, which is WO. So end up your influence line is half WOL. Okay. So this is what they mention here. Yeah. So value of the function caused by a uniform load is equal the area under the influence line X intensity of the uniform load. Okay. So it will be easier if we can go to example 6.7 to see how to use this method, yeah, to draw a influence line for a beam, yeah. So here, determine the maximum positive shear that can be developed at point C here in the beam shown in this figure due to a concentrated moving load of 4 kilonewton and a uniform moving load of 2 kilonewton meter. So there are two types of loads here. One point load and another one is a uniform distributed load, moving load. Okay. Remember, they want to find at C, yeah? Maximum positive shear. Okay. So for shear, we already seen that in example 6.3. Yeah, you can check your textbook. It's already mentioned in 6.3 how to come up with the influence line. Yeah. So the influence line. Okay, here. So this is the influence line at C, yeah. Influence line at C, the influence line for shear at C. So you can check example 6.3 page 241, yeah. Sorry. So this has been mentioned in example 6.3. Okay. So now we want to see what is the influence line for the shear at C. So meaning that you need to consider the effect of shear due to 4 kilonewton concentrated load and also the effect of shear due to this 2 kilonewton. Okay. So based on the diagram just now, you can place the 2 kilonewton, yeah, will occur when the for the 4 kilo, the point load, yeah, is located at X equal to 2.5 meter. Okay. Why we choose this? Because this will create the maximum, yeah. If you refer back, the question asks you the maximum. So if you place your point load 4 kilonewton here, this will create negative. Yeah? This is negative and this is positive. So it will give less force. So no need to put your 4 kilonewton in this area. Yeah? It's better to put 4 kilonewton in the positive area. Okay. So in this case, it's better to put 4 kilonewton at the highest value of shear. Yeah. So in that case, your 4 kilonewton multiply with 0.75. So here. So it will give you 3 kilonewton for shear force. Okay. Rather than you place the 4 kilonewton force at the negative area. Okay. Okay, this is for concentrated force. Now we want to see at which area the uniform load will give the highest maximum shear. Yeah, maximum shear. Maximum moment. Yeah. Okay. Based on this, again, you can see this is the positive area. So it's better to place your 2 kilonewton in the positive area. So you can read here, the uniform moving load creates the maximum positive influence for VC when the load acts on the beam between positive 2.5 and x 10 meter. Yeah, so it's better to put your uniform distributed load just now here along this area from 2.5 to 10 meter. So that's why you need to calculate that area, yeah, the triangular area between 2.5 to 10 meter. Yeah, so this is the area, multiply with, this is the length, multiply with the height, which is 0.75, multiply with the uniform distributed load, and then you get this. So total maximum shear is a combination of 3 kilonewton plus 5.6 to 5 kilonewton. So you will have this value as the maximum shear at C. Okay. So in other way, if you want to check whether your result here is correct or not, you can also do by using a static method of static and method of section, the ones that you already learned in chapter 4. Yeah, so you just place uniform distributed, because you know that the positive area is happen to be in between C to B. Yeah, in this span only. So you just put 4 kilonewton, the point load at this, and the rest of uniform distributed load from C to B. So you just calculate, do the cutting section, yeah. Calculate the VC, cut the section and calculate the VC, and again you will get the VC value is 8.625. Okay. But before that, you need to find what is RA and what is RB. Yeah. So based on that calculation, RA is 10 and RB is, what is RB? Submission moments. Oh, sorry. You need to calculate, not 10. Yeah, you need to calculate that. Okay. So this is the other way that you can check whether your result is correct or not. Okay. Okay, so we have complete chapter 6.1 to 6.2. So I will continue with the rest 6.3 for another videos. Yeah. Thank you. Hope this will help you.